signals or single bit nature of the signal. Okay, this is how a digital engineer looks at any system. So he looks at the timing, the synchronization, the power distribution, the noise, the pin count. He is interested in all of that. Okay, so whenever you look at a system, the first thing comes to the mind is communication. How does the things communicate inside? So if you look at a broader system, the bigger top level system, that it may be a CPU. So there you have multiple ICs put together, and then they would be communicating with each other. So it is a IC to IC communication. Within an IC, there can be a block to block communication. If there are multiple hybrid kind of structure, there may also be a board to board communication, a PCB to PCB communication. So communication has many levels, and at every level issues are different. Okay, my focus is the communication within IC. Okay, my focus is the communication within an IC. An IC is nothing but a digital system with certain inputs and a certain outputs. Okay, so when you go to the off-chip communication, that is maybe IC to IC communication. Okay, then the issues, they become different. Whether you are going for a parallel communication or you are going for a serial communication, because cost matters. Everything is decided by the cost. Okay, naturally when you go for parallel communication, more number of pins are required than when you go for a serial communication. So when you have an IC to IC communication, remember, for an IC, the total number of pins which are taken out, they are always fixed. We never have too many pins coming out of an IC. That is because taking a pin out means you have to have an inside buffer, because the pin is coming out. Okay, so that involves a cost. Extra design cost is added whenever you take a pin out. Okay, so we just want to take a minimum number of pins, that are bare minimum which is required. We do not want extra. So certainly a parallel communication between IC to IC is a strict no-no, because that means too much of a cost. We do not want. Remember, every pin means an added cost. As I said, it does matter. So whenever you have IC to IC communication, it is serial communication. That is data bits. Now it is going to be a bits. Okay, bits, they will be traveling in a serious manner. Whereas within IC, it is a parallel communication, because there actually IC to IC means there would be extra delay also involved. Not only extra cost, there would be extra delay. But within the chip, both the things are not there. It is easy to go for a parallel communication. It is easy to go for a lesser delay with parallel communication. Similarly, but at the end, whenever you have IC communication, ultimately within the chip, because from one IC to next IC to serial communication, but inside that IC there is a parallel communication. So you have to have a serial to parallel converter and parallel to serial. Okay, so this is to take the benefit of both the technologies and to look at the cost minimization. So IC to IC means a serial communication, but then we do require a serial to parallel converter in order to convert the serial data into the parallel data, so that within IC we can leverage the benefits of parallel communication. Okay, so how many pins? So suppose a block is operating at a certain bit rate. So naturally now here we talk of a bit rate. Okay, so bits per second or bytes per second. We talk of bits per second or bytes per second. Okay, so here we talk of a bit rate. We want a higher data rate. When we say a speed, it has a high speed, that means the data rate is very, very high. We talk in terms of bits per second or a bytes per second. More the bits per second, higher is the speed. We always want to achieve a higher and higher bits per second, BPS. Okay. Now, as I said, that parallel versus serial has its own benefits. So this slide which is there on the matter is there, you can find out the various benefits that parallel has over serial, but parallel also has certain drawbacks. Speed is definitely a added benefit when you go for a parallel communication. But then a drawback is that so many nodes are switching simultaneously, because too many outputs are there. One output for every, suppose 8-bit data, I will have 8 pins coming out, or 8 outputs coming out of a block, and all will be suffering a transition, maybe high to low or low to high. So under worst case, if all data outputs are switching, that introduces a lot of simultaneous switching noise within the system. And that also leads to a lot of electromagnetic interference, because whenever two close wires, they are undergoing switchings, that leads to inductive bits. Okay, so that has a lot of noise coming, interference coming from that. So you need to really look into the issues of now interconnect. Laying out interconnects become a problem here, because naturally more number of wires pair, interconnect layout is going to be difficult. That will be one more drawback of going for a parallel communication. Okay, along with the noise problem or EMI interference. EMI means electromagnetic interference. What is ground bounce? Ground bounce means when too many switches, when too many output they switch. So that, because ultimately they all are charging or discharging. Because there are too many charging and too many discharging, that it gives a spike into the VDD. That leads to a spike into the VDD. So VDD either immediately go down or it goes up. So this spike is a kind of a noise. It calls a VDD noise. It constitutes a VDD. So we do not get a stable VDD. We do not get a stable VDD. So this is a problem called as a ground bounce, but it's applicable to both ground as well as the VDD rails. Applicable to both. You need to now here, you need to take care of it. You need to have a very, very high valued capacitor in order to stabilize the VDD values. So there are circuits which takes care of the ground bounce issues. But then it has its benefits. Serial means you will have the less space, fewer device pins will be there, reduced board space requirements, PCB layers will be less, easier layout, low electron. These are all benefits. But then as we know, that bandwidth will be less. So this is, so for a given kind of a design, maybe one block. So how many pins? So for a digital engineer, the first thing is to decide the number of pins to achieve a certain data rate. Okay, what minimum number of pins are required? The first thing he has to decide. Then he will start the design. So going by the specifications, the global specifications, the first thing to be decided is the data rate. So like here in the system, complete system, so you have a cache chip, CPU chip, this is the controller, this is the pin expander, DRAM. It's a complete different blocks of a CPU. And each one is operating at its own frequency. 500 megahertz here, 250 megahertz, 250 megahertz, 100 megahertz, 250 megahertz. Each one is operating at its own optimum frequency. That means now if I say that this is one block, if I say this is one block, or this is one IC, suppose this is another IC, this is third IC, then how many pins this IC will have? If I look at it from that angle, how many pins will this have? How many pins this will have? How many pins this will have? Okay, or if this is a block within an IC, internally it is a serial parallel communication, but it is communicating serially with this block. Okay, so they will all have the lesser number of pins out, but internally it would be a parallel communication between different sub-blocks of this CPU chip. Okay, so how to decide that for this 500 megahertz, for this much VDD 2.5 volts and 80 watt power consumption he requires, how many pins are required? How many pins are required? Okay, so this is a simple example. Before we go for an example, some of the terms that very common in digital jargon. Okay, like here bandwidth is not the bandwidth that we talk about in analog systems. It is different here. Again, bandwidth means a range of frequencies, but in digital domain it is simply referred to as bits per seconds. It is not the same that we talk about in analog domain. It differs. So here bandwidth means BPS or byte per second means 8 bits per second. Okay, and spectrum, analog, we all know we measure analog, bandwidth is measured in hertz. But we do not write bandwidth in hertz in digital. It is always represented as the bits per second or the bytes per second. This is a difference in the same term bandwidth when you refer to it in digital and when you refer to it in analog. So let me go to that small example. So this is the table which shows that for designing this CPU and to get a speed of 8 gigabyte per second, the pins requirement is 128. Okay? And here this is the rate at which you are getting the bits per rate is 500 megabits per second. Per pin. On one pin, the data rate is megabits per 500 megabits per second. So these are the different blocks within the CPU. This is cache data, cache address channels, and in total. So these are some of it, just for the sake of understanding, a sample has been shown here as in the form of a table. So if I want to get the total speed, okay, as 8 gigabytes per second, all I need to do is multiply the rate with the number of pins. So this requirement is 8 gigabytes per second, rate is 500 megabits per second per pin. So number of pins I can count from using this relation, which comes out to be 128. Which comes out, so 128 pins are required. So this will give you a data rate of 500 megabits per second. Okay, per pin. This is per pin. So let us go back now. So once we understand, we know how many pins are required in any digital systems. Now next is all designing inside. So first thing that, as I said, comes to the understanding of a digital design is understanding or designing the timing of the system. I know how many pins I required. I know at what data rate it would be operating. I know the bandwidth of my system. So global things I have set. Now to achieve that, now internally I have to work. Internally the system designer has to work. And internally the first thing he looks at is the timing. Okay, timing means arrival of the data, reception of the data. So that should never go wrong between the two adjacent blocks. It should never go wrong. Otherwise, data moving from previous block to next block, if it gets corrupted, my system is failing. My system is failing. It should not happen. And for that timing, I should look at the signaling, in what way data is arriving, in what form data is arriving. It is periodic, aperiodic, it is a single bit data, it is a dual bit data, dual rail data. I need to look at the signaling approach of my data. Okay. So for timing, there are two very basic methods of timings. Either synchronous or periodic or aperiodic. Okay, periodic, I know very easy that normally there is a clock signal which arrives at a regular interval of time, and whenever it comes, data is moved from one block to the next block. So for this you need to design a complete clock circuitry. Complete clock circuitry needs to be designed. So that timing is a periodic timing. Okay. So here we use a clock source. You require a clock source to determine when the next data is arriving. Data here is a symbol. We call it as a symbol. When the symbol mixes with the timing, we call it as a event. Then it is called as a event. So only data is a symbol. Data, when you add a timing information, it becomes an event. Okay. So here aperiodic means now new symbols or new data will be arriving at irregular timings. In that case, a local clock source will not work. You have to think of some other ways. Only single clock line will not work. Sometimes you need to go for 2 clock lines or you need to go for 2 data lines. Because the next block has to understand that when a valid data is coming, because there may be a possibility that the data line or output line may be having a glitch. So that glitch may be it's just a noise. He has to avoid it. That has to be avoided. So we need to know when the valid data is appearing. And to signal that valid data, I need to have some kind of a reference. If clock is not a reference, then some other way of reference has to be there, which signals that a valid data is arriving. You latch it. You latch it. Okay. So here, You need an explicit transition. Somewhere, I'm not saying only on clock, somewhere you need an explicit transition to signal the arrival of valid symbol. How do you do it? There can be a lot of creativity. And people, they have find out various methods. Okay? In order to arrive, in order to tell you or just to tell the next block that valid data is arriving. So there may be, I don't know whether you understand that dual rail signaling or bundled data signaling. Are you familiar with these terms? Dual rail and bundled data? Okay. No problem. We'll be discussing it. Okay? So, within synchronous also there can be various variations also. Where is a system synchronous? You have a source IC, you have a destination IC. Data is moving from source to destination, and there is a clock source oscillator which is producing a clock, and clock is going to source IC as well as the destination IC. Okay, so whenever clock is coming, it gets the data from the previous block, and this gets the data from this block. So data starts moving at the edge of the clock. So whenever there is a clock, there is a data transfer. Very simple, this method is known as a system synchronous. So a common clock is applied to both transmission and the reception block. Very easy, but then it is very expensive. It is very expensive, and flexibility, there is no flexibility. You cannot change that the time interval is fixed. And that time interval which is fixed, it has to be according to the worst case delay. Because all blocks should be able to transfer the data from source to destination. So whichever is taking the maximum time, that should decide your clock interval. Otherwise, if you have a timing less than that, then it will miss the data. Okay? So that is less flexibility in this, but it is very easy to implement. This system is very, very easy to implement. Fine. Then we have a source synchronous. That is, source does the everything. Whenever, no, here flexibility is possible. That source knows when data is getting transmitted. Final data. So depending on its own delays, okay, it configures the arrival time. It configures the timing of the clock. Okay, so here it controls the clock as well as the data. So when the data is ready to be sent, it sends a clock signal also to the next block, because it is finding an edge on the clock appearing. So for this destination IC, it is a signal that data is appearing. A valid data is coming, it becomes ready to receive it. So here you have a control on the clock signal, and flexibility is possible in having a different transmission interval time. There is a possibility. So output time to the forwarded clock is adjusted so that clock transitions in the middle of the bit cell. What is a bit cell? We will be just discussing. I hope you understand the meaning of source synchronous. Okay? And then we are having a self-synchronous. That is, here we do not have a separate clock. Clock is a part of the data line itself. They both are combined with each other. They both are combined with each other somehow. How do we do it? We'll tell you. So each block, so here destination IC is not dependent on source. It has its own. So the working of this is independent of the working of this. Each one has a similar way. Each one is configured in a similar way. And whenever data is sent, there's a timing information also attached to the data. There's a timing information attached, and then it becomes each block becomes a self-synchronous. How do we implement? We'll see it as we go through the course. So as I said, using a global clock is very, very convenient. Okay? And when we have a global clock, so global clock should it should be sampled in the aperture region surrounding a clock transition. Now what do I mean by that? First of all, for this, understand this. We need to understand how do you understand the timing budget? I'm not going through the previous slides. Let me understand how do we understand the arrival of a data. So data is nothing but a rising transition or a falling transition. Okay. So here we say this is called as an eye diagram. I call it as an eye diagram. Okay. So data, this is the aperture. This is the aperture region where we say there is a valid data. Okay. And this is known as uncertainty. Data may get delayed in arriving. It may not exactly appear here. Okay. It may get delayed this way or this way. So there is a timing uncertainty. This is due to the timing noise, and timing noise is skew and jitter. Delays may come because of numerous reasons. Because there are interconnection delays, there are transmitter delays, there are reception block delays, okay, transmission block delays. Delays may come due to many reasons. We don't know. Similarly, there can be a lot of jitter. That is, a clock aperture also keeps on shifting. Clock edge may not be always stable, always coming at a given interval of time, stipulated interval of time. It may slightly come earlier, it may slightly come little later. So there is a uncertainty in the arrival of the clock edge also. Okay, for me, if this is the data, I should have my clock edge coming at this instant. This is the aperture in which data must be sampled, because for me, this data is a valid data. It may shift here, it may shift here, but as per the timing diagram or the bit eye diagram, this is the aperture region. Okay? So this is my, so ideally I should have my clock edge always at this interval of time. Okay? So now if I am having a 500 bits per second, what is that? We were having system is operating at 400 megabits per second. Okay? That means the bit cell time is, you can convert 2.5 nanoseconds. Okay, that means you have a timing interval of only 2.5, then the next symbol will come. The next data will come. So between two data, I have a difference of only 2.5 nanoseconds. So for me, the T-bit or bit cell bit interval time is only 2.5 nanoseconds. And you see the next data is starting after that. The next data is just previously is shown like that. Half the portion is shown. Okay. So I can have only time duration available to me is only 2.5 nanoseconds. Within this, there would be a certain time taken by the transmitter. It will take some rise time and fall time, because it is nothing but a combinational block. There would be certain rise time and a fall time. So it is that rise time. 1 nanosecond rise time may be there. Okay, data may be rising, data may be falling. So there is a rise or fall time associated both ways. Even receiver will also have a rise and the fall time. Okay, and then there is a uncertainty. There is an uncertainty, timing noise come into picture. I have to take care of that timing noise. That's an uncertainty. I don't know how much my data will delay. I don't know. So if I have the a priori information about the timing noise, I can design my bit cell. I can design my eye diagram for a data rate of 400 megabits per second. I can design. So my T-bit, this is how the eye diagram will look like. I will have, suppose my timing noise is 600 picoseconds on both the sides that I am taking care of, and there is a 1 nanosecond rise time totally, and there is, so I will have equal space. My data will be, the aperture region will be equally spaced. Okay, so I will be having a 600 picosecond here, 600 picosecond here, 300 picosecond aperture region, and then 1 nanosecond of my rise time or the fall time of my transmitter or receiver. This is known as the ideal eye diagram. Ideal eye diagram. Okay, so this is how we start with for understanding the timing property of my digital system, which is operating at a data rate of 400 megabits per second per pin. So this is for one single pin. Okay, ideally I want my data to be sampled because this is my valid. This is uncertainty. I may not be valid data for me, may not be valid data for me. How to take care of these two regions we'll be looking at. Okay, clear? The period is over. Has the bell rung? No. No? No. Fine. 5 minutes. Actually, what you get is this. Actually, there you are showing you can say many signal waveforms over many cycles. I diagram for many cycles. So actually, this is what you will be getting. So it's not that there are no uncertainties keeps on changing. Rise time, fall time is data dependent. Rise time and fall time is also data dependent. Input pattern dependent. So worst case I'm taking, but it can always change. Similarly, delays are also, uncertainties are also input pattern dependent, input combination dependent. So if you keep on running the simulation for many cycles and then just superimpose all the t-bit cells one over the another, practically you will get this kind of a eye diagram. Where you can say the signal waveforms over many cycles has been superimposed. Okay, this may be how you look like. How does it look like in it? When you run a transient analysis. When you run a transient analysis. Okay, going high, signal going high, signal going low. One pin means, or one output means one node, one data node, one data output. So it may be going up, waveform may be going up, or waveform may be going low. Okay, so in terms of eye diagram, this is how it will look like. And for me, the opening of the eye is very, very important. Opening. How much is the opening? Both ways. Vertically, maximum opening. Horizontally, what is opening? Okay, you can very easily understand the voltage and the timing uncertainty. So horizontal variation is given by this horizontal opening. And the vertical variation gives you the voltage uncertainty, and this horizontal variation gives you the timing uncertainty of the signal. So voltage level is also shifting. It is not always reaching VDD. It is not always reaching VDD. Signal is not always reaching VDD. So you have a voltage uncertainty. You also have a timing uncertainty. Sometimes rise time is more. So entire bit cell is shifting towards the right or shifting towards the left. Okay. So it immediately gives you an indication of voltage and timing uncertainty. So when we look at these horizontal and vertical eye openings, we tend to know how wider your eye. I want eye to be as wide as possible, opening to be as wide as possible. That means lowest possible or least possible uncertainties. Okay? More hazy is this, smaller is the eye opening, more the uncertainty, less robust is the communication. System is going to fail. There is a larger probability system may fail because of timing uncertainty. Okay? This is the actual waveform, picture of a snapshot of an actual waveform obtained on an oscilloscope. So can you see that here you have a very clean, very wide opening, whereas here the eye opening is very, very small. Uncertainty is very, very large. We certainly do not want a system like this. Nobody wants a system like that. It should be as clean, as wide as possible. So you can just go through that. Size of the eye opening in the center of the eye indicates the amount of voltage and timing margins available to sample. Vertical thickness gives you AC voltage noise. Horizontal thickness gives you AC timing noise or jitter. And the margin rectangle with width equal means larger the margins, larger the length means your signal has adequate margins. More the margin, lesser is the chances for a system failure. Okay, so this lecture is actually not from the Rave's book, let me tell you. It is taken from a book, Digital Systems Engineering by Daly and Bolton. So I have a soft copy. You may get it from the internet, or if you don't have, you can take it from me. I don't have